All right. So as I was saying, I haven't had a chance to check all of the all of the identities that are necessary for this to be correct. Um, Mostly, what I want to do is to, I mean, there are a lot of them that work out nicely, but there's a lot of surface area to check. Um, but there are some very intriguing analogies between the rho-calculus and quantum mechanics that make that make it, like too tempting to not leave to leave unexplored. And also, there's this long history now that goes back several decades of a desire to have an axiomatic presentation of quantum mechanics. What I don't know if people here know, but there are like many presentations of quantum mechanics, right? There's the Schrodinger presentation, the Heisenberg presentation, the Dirac presentation, the Feynman presentation, and in each of those presentations, there's a kind of there's a piece of the puzzle that it's not tidy, if you think about it, because it's hard to say what part of the ambient mathematics is necessary and what part is just quantum mechanics. And so there was a movement to try to present, the axioms that would characterize quantum mechanics as quantum mechanics. So I actually worked with Samson Abramsky, not on this, but on other things that are closely related. But Samson was one of the major proponents of axiomatic quantum mechanics, and he worked with Bob Kuka, and they developed a categorical version of quantum mechanics that has a lot of promise in it. So if you're interested in that, Bob Kuka and Alex Kissinger, one of his collaborators, wrote a book called Picturing Quantum Processes. And that tells a lot about the development of that line of research. But I'm going to talk about a different line of research that has to do with, the process algebraic side, and in particular, what makes rho very different from the other process algebras. That makes it so intriguing. A disclaimer: I'm not a physicist. I don't even play one on TV. So I have only a rough mathematical understanding of quantum mechanics, and I would never claim to have physical intuition around quantum mechanics. Of course, a lot of physicists said that nobody has physical intuition around quantum mechanics. So maybe I'm in good company. I don't know. But the idea, the analogies that I want to cover are the fact that you can kind of think of names in the rho calculus as scalars. You can think of processes as vectors, and you can think of contexts as duals to vectors, or linear operators of some kind. So to begin this, we just want to point out that because names are coded processes, they inherit all the algebra processes. So for example, we can define parallel composition on names, and that's just basically redistributing the operations so that, the parallel composition of at P with at Q is defined to be at P par Q, right? And you can lift this to really complex operations like this square root operation that I defined before, a year ago, right? So the square root of a name is just the name of the square root of the process that is quoted. So it's pretty straightforward, this process of redistributing the operations. I want to point out that there's because of this, there's an interesting notion of the multiplication of a name to a process. So if we were going to have, names function as scalars and processes function as vectors, then you can multiply a vector by a scalar, right? So we'd like to have an operation that's kind of like that. And there's one that works out fairly nicely. So what you do is you take all the free names. So if Q is your process and at P is your name, then the multiplication of at P times Q is just going to be take Q and you replace all of the free names with in Q with the parallel composition of that name with at P. So you're basically just shifting Q over into this other namespace where you've added at P to all the free names that Q is using. Hopefully that's clear. Does that make sense?
So we are like moving the whole range of names.
All the names. Yeah, all the names in Q, all the free names in Q are basically, you know, being shifted over because you're adding at P to all of it. Parallel composition of at P to all of it. All right, so that's clearly well defined. We just defined the parallel composition of names, right? That yields a name. And so we're taking a name and replacing X with that name, right? And we're doing that substitution uniformly throughout Q. Okay, so that's fairly straightforward, not very hard. One line equation. And it turns out that these definitions have nice properties, right? So if you take at P and you parallel compose it with at 0, well, that's just at P, right? So 0 is acting as a kind of unit. And the same thing is true you know, if you take at 0 times P, you just get back P, right? Because the parallel composition of 0 with anything is just itself. And so if you substitute, you know, parallel composition of at 0 with, you know, X, that's just going to be X. So if you replace all the free names X and P with themselves, you just get P back, right? So that's that identity is obvious, right? So at 0 is forming a kind of unit, which is very nice. So what we're going to do is henceforward we're going to treat this as a notion of multiplication, right? So we're just going to define the multiplication of names to be the parallel composition of names, and define the multiplication of a name times a process as before, right? So now we have a notion of multiplication, and it seems to have some good properties, right? It's associative, it's commutative, it has an identity. It looks like a multiplication, right? Now you can do something very similar with context. So context, as you recall, is a process with a hole in it. So here's an example of a process with a hole in it, right? We have P parallel hole. And we're gonna use that construct in a minute, but that's an example of a hole. And the application of a context to a process, you just put the process in the hole. Right? So we're gonna define this kind of dot product or inner product like operation to be the name of the process where you take P, you stuff it in the hole of K, and you perform the substitution. So the substitution is you're going to shift all the free names in K, X, right? All the X's that are free in K by at P times X. And you're going to shift all of the free names Y that are free in P by at K of 0 times Y. Okay, so we're shifting them over. And now if we take this definition here, so the transpose of a process, like the transpose of a matrix or the transpose of a vector, turning a row vector into a column vector, right, or flipping a matrix around, right, is just going to be making the context P par whole. Okay, so this is like the transpose operator. And notice that this gives us just the right kind of equation, right? So if we take P dot Q transpose, then what do we get? Well, we're going to get P par Q, right? That's K of P. So K in this case is Q transpose. So that's going to be Q par whole. And par is commutative. So it would be Q par P, but par is commutative. So you don't care about that. We're going to take the name of that as per here. We're going to take the name of that. And then we're going to do this thing. So at P times X for the free names in Q transpose, right? And at Q times P. Now notice that at Q applied to 0 is just Q applied to, Q par 0, which is just the same as Q. So this is just going to be at Q times Y, substituted for Y in P. So we're sort of shifting the Q part over by P and the P part over by Q, right? And notice that we can also define a multiplication for duals or linear operators, right? Just like in linear algebra, we can do that, and it's just basically push the multiplication through and then take the transpose. Nothing fancy. Again, all of this stuff is like kindergarten, right? There's not a lot of really hard thinking that has to go into these definitions. But so now let's start to take a look at what this might mean if we were going to interpret this from a quantum perspective, right? So I think most everyone prefers the bra-ket notation. So this is the notation developed by Dirac in his presentation of the quantum mechanics. So in that, vectors are kets, right? So this is a ket, right? And we're interpreting processes as vectors, right? So we're just going to take the ket notation, just yields back the process. The bra notation, which is supposed to give us the linear operator, is going to be the transpose of the process. Okay, and then when you do the bra-ket operation, that's going to be P dot Q transpose. So that's the idea. Oh, I think I've got that flipped around. It should be Q dot P transpose. Sorry, that's a typo. If I have Q in the ket, the bra position, and P in the ket position, that would be the right definition. So I'll fix that. I can fix that now. So it should be Q transpose. There, like that. And the way to think about this is, like if you're familiar with quantum mechanics, then this kind of thing, here Q is in the, oh, did I screw it up again? Yes, I screwed it up again. I got that wrong.
Yeah, you just switched
Sorry.
the order of the terms, but it needs to be P to the
P
T and then Q.
Yeah, that's right. Yeah, I totally screwed up. Yeah, there we go. Okay, sorry about
P
that.
transpose, yeah.
There you go. So that's so the way to think about this in the physical interpretation of this notation is Q is some vector, some representation of the state of the quantum system, and P is some observable that you can measure or observe of the system. And this thing gives you, when you do this calculation, it gives you the probability amplitude, right? So the probability that we make that measurement of that state is going to be the square of this thing. That's the physical interpretation in quantum mechanics, right? So that, and now just a brief aside. So that's essentially the Born rule, right? What's interesting is that idea of a probability amplitude and a notion of probability. Well, if you check that notion of probability, like so there's like the physical intuition as to why that's a probability. And that's just an intuition, right? There's nothing we can prove about that except by checking experiment and seeing if repeated measures give us distributions that line up with the predictions of the theory. And so far, it has been in exactly that way. However, you can also ask mathematically, right? So there are two, at least two, axiomatic presentations of probability, right? So there's the frequentist axiomatic presentation, and there's the Bayesian axiomatic presentation. And what you will find is that the probability that you get using this mathematics is neither. Nobody ever talks about that. Nobody ever talks about, well, sorry, it's not true. Scott Aronson does talk about this. But in general, it's not a very popular notion that this formulation of probability is distinct from other axiomatizations of probability, right? So the physicists just kind of pulled an idea out of their hat, right? Which is perfectly legitimate, perfectly reasonable, especially if it gets you a predictive theory. But what they didn't do is go back and check if that was in fact, you know, a mathematically well-defined notion of probability, a la, you know, other axiomatizations of probability. And it turns out that it's a distinct axiomatization, which suggests to me that probably, you know, that's a better axiomatization because it's the only notion of probability tested against physical phenomena so heavily. And so I would recommend that probability be founded, that the foundations of probability should be on this version of linear algebra rather than the way either the frequentists or the Bayesians put it forward. So any questions so far about anything I've said?
Well, I mean, this sounds actually a little bit closer to the Bayesian axiom, and I wonder how much of a difference there is between the Bayesian and the
oh no, it's
and this formulation.
Definitely not, because you have you have linear things going on that are not supported in the Bayesian. And in particular, you can have negative probabilities. You can't have that, right? You can square a complex number and get a negative number. So yeah, no, it's not Bayesian. And you can check it, right? Just go check the math. Don't take my word for anything. Check the math. But anyway, any other questions before we move on? All right. So then you can check immediately from the definitions I just gave that we preserve the identity that if you were to take, so since you know, ket q is just a process, and if you have some name and you multiply it by q, that's going to give you another process. So that could be another, you could think of that as another ket, right? And so you could then take the dot product with the transpose of a p. Since we already have a definition of a name times a bra, we can check that both sides of that equation down there yield the same thing, and in fact they do. So that's nice, right? And we're starting to get the same kinds of identities that we expected, and that we demand if it's going to be a reasonable interpretation of quantum mechanics. You can also check, you can look for an outer product, right? So we've defined an inner product. You can look for an outer product, and this outer product is really important if we're going to ultimately talk about entanglement and things like that. And so if you have two kets, you'd like to be able to multiply them together. And so that should yield a process, not a name. This provides a definition. It's very similar to the one we gave before. We're not using contexts, right? So you multiply the free names in P by at Q, and you multiply the free names in Q by at P. Very similar to the definition, right? but you can check that it does in fact satisfy this definition, right? And the reason is because this is going to put C or X, whatever, you know, if I let C range over names now, this is going to put C in all the free names in P, and then I'm going to multiply that this way, oh, huh. I need to look at that a little bit more carefully. I'll check that offline just to make sure that that works out. I spotted something that's a little bit funny there. I'll go check that offline. But at least yesterday I convinced myself that that goes through. So notice that if we just look at the inner product gadget, as I said, that's a square of probabilities. Then that means that we'd have to square it. Now we have a notion of multiplication, right? So this is a name, and squaring it is that name times itself, right? We can expand that, and then we can expand this, and right. So it's the name where you have all the free names in P multiplied by Q, all the free names in Q multiplied by P, right? And we're squaring that, right? And then so then we can rearrange these so that we flip this one and this one, right? So we'll get the Q's to one side and the P's to one side, and so that's what gives you that. So it's an interesting calculation. I don't know that it gives us a sense of numeric probability in the same way that, you know, real numbers give us a numeric probability. The connection between the kind of quantitative interpretations that we get from, you know, the reals and rho-calculus like processes is interesting. By the way, you can expand the rho-cal in the same way that Conway games expand to give you all the reals and the surreals and all of that. You can expand the definitions of the rho processes. So there's a lot of, there's two major gadgets that you can do to get uncountable number of processes. So one is you allow for infinite branching in the par, so you can have infinite parans. And the other is that you allow for fixed points in the names. So in the ordinary rho-calculus, the names have a finite depth to them. You can only go as far down as 0, and then you stop. But you can give name equations that are fixed points. So you can go infinitely deep, and you can also allow for infinite branching, so you can go infinitely wide. And those two tools will get you uncountably many rho processes. And once you have uncountably many rho processes, you can use them to encode things like Conway games. And since you can encode Conway games, you can have the real numbers. So the idea of using the rho-calculus in this fashion to represent things that we normally represent with reals or complex numbers is not nearly so far-fetched as it might first seem. I'm not proposing that we use only computable numbers, although that is also a very interesting question to go and look at. But it's possible. It's possible to expand the rho-calculus in such a way that these names are yeah, it can be put in one-to-one correspondence with the reals. So this idea of modeling probabilities is not nearly as far-fetched as it might seem at first. There are two other points I want to make about this exercise. So the first idea is that we can. So it's typical in physics to label kets, to have a labeling scheme on kets. So you denote the states by their labels, right? Like spin half, spin minus a half, that kind of thing. Now we have something that's even more fancy. In particular, we have the types that come from operational semantics and logical form. And that gives us an ability to produce labels that don't just define a single state, but instead define sets of states. And in fact, they can also define sets of linear operators. So we can lift all of these interpretations through the logic construction. And so now we can define whole classes of behavioral constraints, quantum behavioral constraints, assuming, of course, that this that that all the identities and stuff could eventually check out. So let me stop there because that's a lot to digest, all the things that I just said. Any questions about what I just said?
I think you may have the same type on this page as the previous ones, right?
Yeah, I do. You're absolutely right. Sorry.
Can you say a little more about? I mean, I'm not sure that I understand how these calculations are done with reals. So I'm just wondering, with encoding in rho-calculus, we are using operational semantics of rho-calculus to do the same calculation, but this encoding gives us a different view, right? I mean, I'm not sure how can I.
So you're right on the cusp of the other thing I was going to say, which is that so far we've only used the structural aspects of rho to encode these calculations. We haven't used the time. So what we need is an analog of the Schrodinger equation, which talks about how things evolve in time, right? That's the thing. But the thing that's really awkward about the Schrodinger equation is that's what gets it into trouble. I need to be a little careful. The Schrodinger equation mentions time outside of quantum mechanics. That's the way to talk about it, right? So that would be the first place I'd look if I were suspicious about the way quantum mechanics and general relativity work together. Is having the time evolution of the system be outside like that. That's weird, right? If time is going to be quantized, then you need that to also be quantized, right? Because we're talking about quantizing space and time, so that evolution. So there has to be a corresponding notion of evolution of the system that is related to the operational semantics, right? So far, we've only mentioned the structural piece. So if we want that, then what we have to do is to look at this as a probability, this inner product, and relate the inner product to the probability of taking a reduction step. And I haven't talked about that because that is quite a bit trickier. That requires a lot more thought. But that's the idea. Yeah.
So can we say that you say that time is like we are having some language, and we have some additional stuff that is doing in the background, which is not represented directly in the language, but we need this for our language to like to express the dynamism in our language. And with rho-calculus, we can do all of these things inside the language.
Correct.
Can this be like naive?
That's exactly right. That's precisely the idea. So if you look at the Schrodinger equation, right? The Schrodinger equation is, you know, d wave function dt, right? That's one side of that equation, and so that derivative with respect to time is talking about the time evolution of the system, but that's not inside the quantum mechanical interpretation, right? It's sort of, it's on the outside of the mathematics, so to speak, right? It's if you're yeah, how do I say this? Right, the axiomatization of quantum mechanics needs to include the notion of time evolution in the system, and that isn't typically done, right? The time evolution is on the outside of that. Whereas here, you know, the operational semantics, the COM rule, is in fact on the inside, right? And the COM rule is what's going to take and run these parallel compositions, right? So that's what's even more intriguing about making this, you know, getting a version of this program that nails all the identities, right? Gets the math lined up, you know, so that on the row column side and on the linear algebra side, they're one and the same. Yeah. So very good question.
Thanks for the answer.
No.
This clarifies a lot. Yeah. I mean, I'm thinking that we can put lots of particles together and they will do the magic. We don't need to like external force to say, oh, now you have time, you do something, right?
That's exactly right. And the flip side is also true from the point of view of general relativity. Right? General relativity is requiring that you have this team of surveyors that are laying down these charts, all these maps all over the universe, right? Yeah, it's like, that's no good, right? That has the chart system has to be a part of the universe, right? It doesn't get to be outside of the universe, right? So that's the thing that's on. So like, if time evolution is on the outside of quantum mechanics, then the framework of rods and clocks, right, that Wheeler talks about in his books, right, that has to be a part of the universe too, right? And so all of those things are also subject to both general relativity and quantum mechanics, right? All of those constructions have to be inside the system, not outside of the axiomatization of the system, right? And so in particular, wall clock time is not compositional. That's the problem, right? Whereas we have a notion of, you know, this step evolution in time that comes from interaction. So again, that's more natural, and it's more, you know, self-contained, so to speak. Again, you know, we're very, very far from being able to calculate, you know, how the spin of, you know, how the spin of a silver atom is affected when it passes through certain observations. You know, we don't have that yet because it's hard to get one's head around the notion of probabilities as represented by these rho-calculus processes. So this is, you know, this is still very much a toy, but it's a fun toy, and it opens up, even at this level, it opens up the kinds of questions that we've been talking about right here. So,
Is it make sense to think, because our notion of time is linear? I mean, yeah, maybe. Yeah, I'm not sure if in quantum mechanics this is like true, but I'm thinking that maybe is it possible that this probability becomes more accurate or different, like different when we don't include time initially, where we are floating together with the reductions. So from that perspective, maybe probability is not really a probability, but we can say more correctly what's happening.
well, I mean, I honestly think that we're, you know, if we go the route of thinking about race conditions as giving us the fundamental non-determinism, right? We like when you have a par, when you have actual true concurrency, right? Then what these probabilities will do is they'll give you conditions on which interactions are going to be more likely to happen.
I see.
Yeah, so that's the way to think about it. So, and that relates to, remember I said there were two things I wanted to mention. So the other thing that I wanted to mention is that this notion of squaring, there's another notion of squaring that we might want to look at. So remember, I defined the square root of a process, right? So the square root of a process is related to the fault tolerance of that process, right? So it's two processes that when run in parallel will give you the original process, right? And I define this way of, you know, taking two copies of the process and having them, you know, flip a coin as to who gets to go. And that just works, right? The math of that is very easy to check. So we have some kind of confidence in that. So we could say, if I've got a process, is it the square root of some other process? Right? You can inspect a process and say, hey, is this a square root? And if it is a square root, then you can calculate the square. You can undo the square root operation, right? And that might be another notion of squaring that we could employ here. But then you would have to reconcile that with this multiplication here, which might rejigger some of the definitions all the way through. I haven't gone down that path, but it's that path of research, but it is well worth thinking about, just to check and see if there's something along those lines that might be worthwhile. Does that make sense? Do you get what I'm talking about there?
I'm not sure that I'm completely following, but I think I
well, it's a really simple idea, right? So like we can define the square root of a process, right? So,
yeah.
So can we define the inverse of that operation? So if I have a process, can we detect that it is the square root of something, and give that something back. So that would be squaring.
I see.
Right. And so, and then the question is that notion of squaring, well, we can calculate that notion of squaring is frequently different than this notion of squaring. So the question is, you know, maybe we should use that to square the probability amplitude, because it's now very closely related, right? Because, you know, we're getting these copies of processes, right? That is starting to look like the square root of a process because we're getting copies, right? And so maybe there's a notion of you know, reducing the, you know, undoing this copying. You see what I'm driving at now? So if these are all redundant, copies, then maybe what's going on is to calculate the likelihood of an execution. You kind of lift up out of the forest so you can see the trees, right? Or lift your gaze from a particular tree so you can see the forest, which is that, you know, there's really just one process here that wants to take a step, rather than a bunch of copies that are all going to be synchronized in some way. So anyway, it's just an intuition. It's just a thought, not something that I've reduced to calculation. But the one that I think is really interesting, the one that's most interesting, is using the types to label these bras and kets. That starts to get fascinating, because now we can talk about classes of quantum interactions, which has a lot of power, right? So you can talk about classes of states, right? That sort of thing. All right. Anyway, so that was all I wanted to chat about today. Any questions or comments?
I have a question about what you said previously, and maybe you can relate to this about agency. And I'm not sure how to think about that, especially when you talk about like very fundamental things.
Okay, so yeah, right. I think it's, you know, it's relatively straightforward to grasp that a process is intended to represent a particular aspect of agency, right? So if you go back to Robin's original intuitions that allowed him to formulate the axioms of CCS and then the pi calculus, right? He's thinking of a process as like a computational unit. But this computational unit is interesting because it's fractal, right? In the same way that, you know, a tree is fractal because the leaves look like trees, or a forest is somehow fractal. So or you know, the human body, right? The cells are autonomous entities, right? They live lives on their own, that's connected to the life of the individual, but they are autonomous, right? And so processes reflect a kind of agency in the sense that they have a notion of autonomy and they have a notion of interaction. And that's what trips up both general relativity and quantum mechanics, because they don't have a notion of autonomy. There's always some God's eye view, right? In particular, the God's eye view in the case of quantum mechanics is the time evolution. There's something that's on the outside that's running the clock that says how to advance the system. That's on the outside of quantum mechanics, right? That's the God's eye view that's implicit in quantum mechanics, right? And in general relativity, the God's eye view is this chart structure, right? The chart structure is given from the outside, and in fact, it's much worse, right? Because the Einstein equations, you have to know the stress energy tensor from the outside. You have to know the distribution of matter and energy throughout the entire universe. That's not science, right? Because people are not going to do that, right? You need to build up local descriptions and piece them together, right? And you have to have rules about how it's reasonable or when you can piece descriptions together, right? And that's where this notion of autonomy and interaction are so important. So it turns out and also this notion of agency is missing, right? It's missing from quantum mechanics. We don't talk about the agency of a quantum system. We don't talk about the agency of a gravitational system. But as you climb higher and higher the levels of complexity, right? By the time we get to systems that have immune systems and pathogens and viruses and that sort of thing, it is next to impossible to describe those systems without using words like purpose. Right? The purpose of the immune system is to defend against viral attacks and bacterial attacks and other kinds of pathogens, right? It's very, very difficult not to talk about those kinds of systems without using the words telos and purpose, right? And that's because we can easily see the notion of agency. And so the question is, when does that notion of agency creep in? Does it show up on top? And what I've been trying to argue is that that's intellectually sloppy, that the notion of agency needs to be factored in at the very beginning. So you start with the notion of agency, which basically boils down to notions of autonomy and interaction. And then you build up these other complicating behaviors like quantum mechanics, which this is an attempt to sort of sketch out how one might go about that, all right? Or general relativity. And again, I've given variations of calculi like this that allow you to talk about space and time. Right, so you start with the notion of agency baked in, right, and then you build things like quantum interactions with non-determinism and evolution in time, evolution in space on top of that, and then you can get more and more complex behavior, but agency was always there from the beginning. Does that make sense?
Yes, yes. So when we have this God's eye view, we're basically saying there is only one agency from this aspect. So
yeah, you're placing the agency outside of the system, which is not good. That doesn't work, right? From a mathematical point of view, I mean, literally just from a software engineering point of view, it's a bad choice.
Yeah.
But it's a natural choice. If you look at the history of human thought, it's a natural choice. It just kind of gets in the way of building these systems, right? So Rao, if you are interested in sort of how quantum mechanics is different from Bayesian stuff, I heartily recommend the lectures of Scott Aronson on how quantum mechanics is just probability with negative probabilities.
Okay, yeah, thank you.
Sure. Yeah.
Scott Aronson, A-R-O-N.
Yeah, that's right.
Okay.
Yeah, very, 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 very entertaining. He's incredibly eloquent and humorous. Yeah, so well worth the engagement.
Great, thank
sure.
you.
Sure. No, it was a good question. It was a good question. I just, yeah, my colors were showing. I have I'm not a big fan of Bayesian.
Well, no, I mean, when I was comparing it to Bayesian, certainly the formulation that says, you know, P given Q is more similar to Bayesian than the frequentist. So I was thinking, my curiosity was to say, well, how much of a difference there is, but you were saying there is like quite a bit of difference. So I'll listen to his lectures. Yeah.
Yeah. Coolio. Well, I guess I'll see some of you in Dev Stand Up in about 5 minutes. I really appreciate the time and the opportunity to present some of these ideas.
Great, thank you, Greg.
Thank you.
Thanks.
Thanks, Greg. Thanks, everybody.